Hello everyone. In this video, we are going to discuss about electronic configuration of atoms from the chapter 2 structure of atoms class 11 chemistry. You see, the distribution of electrons into orbitals of an atom is called its electronic configuration. So what is an electronic configuration? The distribution of electrons into orbitals of an atom, that is actually called as electronic configuration. See, if we have the idea of the basic rules, Aufbau principle, Pauli exclusion principle, Hund's rule, which govern the filling of different atomic orbitals, the electronic configuration of different atoms can be written very easily. See, we have already discussed about the Aufbau principle, Pauli exclusion principle and Hund's rule in our previous video, which is available in the playlist. So you see, the electronic configuration of different atoms can be represented in two ways. One is S raised to A, P raised to B, D raised to C notation. Then another one is orbital diagram. See, S orbital, P orbital has, actually it has it is a degenerate orbital, no? Px, Py, Pz. Okay, similarly we have D orbital, which is also a degenerate one. 5 orbitals having the same energy in the case of D orbital. Okay, that is you see in the first notation, that is why here we have 5 boxes. Okay, here we have 3 boxes. And S orbital, it is not a degenerate one. That is why we have only 1 box here. Okay, so you see in the first notation, S, P, D, they are actually the letter symbol of subshell. And the superscript A, B, C, that is actually the number of electrons present in the subshell. That is if I write 1s2, that means S is the subshell in which we have 2 electrons. Okay, if I write 2d4, we have D subshell, principal quantum number is 2 and we have 4 electrons in this subshell. Now you see in the second notation, orbital diagram, each orbital of the subshell is represented by a box and the electron will be represented by an arrow like this. Okay, see, electron with the positive spin is represented like this and electron with a negative spin is represented like this. See, the advantage of this notation, that is the second one, orbital diagram notation, over the first notation is that it represents all the 4 quantum numbers. See, let us consider the hydrogen atom. Its atomic number is 1. So its electronic configuration will be 1s1. Okay, it means that it has only 1 electron in the 1s orbital. So its orbital diagram will be, you see 1s. So the orbital is represented with a box. Okay, that subshell, the S subshell is represented with a box. Only 1 electron is here. So we will represent it like this. Okay, now if you consider the helium atom, its atomic number is 2. So its electronic configuration will be 1s2. Okay, that is, it has 2 electrons in the 1s orbital. The 2 electrons will differ from each other with opposite spin. So its orbital diagram will be 1 spin up, another 1 electron spin down. This is the 1s orbital. Now if you consider the case of lithium, its atomic number is 3. So its electronic configuration will be 1s2, 2s1. Okay, so you see there are 2 electrons in the 1s subshell. Okay, the 2 electrons will be, they will differ from each other with opposite spin. So 1 spin up, 1 spin down. Then you see the third electron of the lithium, it is not allowed in the 1s orbital because of Pauli exclusion principle. So you see, since the third electron of lithium is not allowed in the 1s orbital because of Pauli exclusion principle, it therefore takes the next available choice, that is 2s orbital. So the third electron will be here in the 2s orbital. Okay. So now let us see the orbital picture of elements. That is, if you consider the hydrogen, its atomic number is 1. So its electronic configuration will be 1s1. So only 1 electron is there in the 1s orbital. So the orbital is actually represented with a box here. Only 1 electron is there in the 1s orbital. So 1 electron, which is just like spin up. Okay, now if you consider the helium, See, He24, no, helium. So atomic number is 2. Its electronic configuration will be 1s2. So there are 2 electrons in the 1s orbital. One spin up, another one is spin down. Okay. Now if you consider lithium, its atomic number is 3. So 1s2, 2s1. Okay. So 2 electrons in the 1s orbital, 1 electron in the 2s orbital. Now beryllium atomic number is 4, so 1s2, 2s2, that is the electronic configuration. Because s subshell cannot have more than 2 electrons, so maximum 2, here in 2s also maximum 2. This is the order of energy levels or orbitals, so that is why we are writing it like this, 1s2, 2s2. So you see 2 electrons in the 1s orbital, spin up, spin down, 2 electrons in the 2s orbital, spin up, spin down. Okay, now if you consider boron, atomic number is 5. So 1s2, 2s2, 2p1. That is the electronic configuration. So 2 electrons in the 1s orbital, 2 electrons in the 2s orbital. Okay, both should have different quantum numbers now. So at least their spin quantum number must be different. So if one is spin up, another one should be spin down. Then 2p1. Only one electron is there in the 2p orbital. So you see, we know that p orbital is actually divided into px, py and pz. All the three are actually having the same energy. Okay. Now carbon atomic number is 6, 1s2, 2s2, 2p2. So 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, then 2 electrons in the 2p orbital. Because according to the Hund's rule of multiplicity, first the electrons will be occupying singly and only after that they start pairing up. Okay, now if you consider nitrogen, atomic number is 7, so 1s2, 2s2, so 2p3. Okay, so 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, 3 electrons in the 2p orbital. Okay, now oxygen, atomic number 8, so 1s2, 2s2, 2p4, 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, then 4 electrons in the p orbital, no, 2p. So first they occupy 1 electron per orbital, just like that. Then after that they start pairing up. Here we have 4 electrons in the 2p orbital. So 3 are here, now 4th one. Okay, now if you consider this fluorine, its atomic number is 9, so 1s2, 2s2, 2p5. So 1s2, 2s2, 2p5. So 1, 2, 3, then pairing 4, 5. Okay, now neon atomic number is 10, so 1s2, 2s2, 2p6. So 1s2, 2s2, 2p6. So first 1 electron per orbital, then pairing 1, 2, 3. Okay, so you see, this is the orbital picture of elements. So you see the electronic configuration of neon is 1s2, 2s2, 2p6. You see, the process of writing the electronic configuration that can be simplified if you represent the total number of electrons in the first two shells, that is in the 1s, 2s and 2p subshells, by the name of the element neon. That is, see, for neon its atomic number is 10. So electronic configuration 1s2, 2s2, 2p6. Okay, 1s2, 2s2, 2p6. So 1 electron per orbital, then pairing up 2p6. This is the orbital picture of neon. Now if you consider the next element sodium with atomic number 11, its electronic configuration will be 1s2, 2s2, 2p6, then 3s1. Because p orbital can have maximum of 6 electrons, so the 11th electron will go to the 3s orbital. So you see, this 1s2, 2s2 and 2p6, this is the electronic configuration of neon, no? So this is the electronic configuration of neon. Then after that we have 3s1. That is, the electronic configuration of sodium can be written like this. Okay, that is, instead of writing all this, you can just write like this. That is, the writing of this thing can be simplified by using this thing. Okay, now if you consider argon, its atomic number is 18. So 1s2, 2s2, 2p6, 3s2, 3p6. That is the electronic configuration. So 1s2, 2s2, 2p6, this is the electronic configuration of neon. And we have 3s2, 3p6. So instead of writing all these things, you can just write like this as the electronic configuration of argon. Now you see the electrons in the completely filled shells, that is actually called as core electrons. The electrons in the completely filled shells, that is actually called as core electrons. So for neon atom, we have all the shells are completely filled. See, F subshell is filled because maximum number of electrons possible for SS2. This is also completely filled. And for P subshell, the maximum number of electrons possible is 6 and it is also completely filled. So the electrons in the neon are core electrons. Okay. Now you see the electrons that are added to the electronic shell with the highest principal quantum number, they are actually called as valence electrons. The electrons that are added to the electronic shell with the highest principal quantum number, that is actually called as valence electrons. For example, consider the element carbon. Its atomic number is 6. So its electronic configuration will be 1s2, 2s2, 2p2. Okay, 1s2, 2s2, 2p2. So in this case, the highest principal quantum number is what? 2. See, here 1 is the principal quantum number, here 2 is the principal quantum number, here also 2. So the highest principal quantum number in this electronic configuration is 2. So the electrons in the 2s and 2p orbitals, they are actually valence electrons. Okay, so carbon has 2. 2 plus 2, 4. 4 valence electrons. 2 in the 2s orbital and 2 in the 2p orbital. These 4 valence electrons, 2 in the 2s orbital and 2 in the 2p orbital, these 4 valence electrons are involved in chemical bonding, making carbon an excellent element for forming molecules and compounds such as organic molecules and carbonates. Now let us consider an element scandium. Its atomic number is 21. So as per the Aufbau principle, the order of energies of orbitals, that is actually like you see 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, etc. No? So here the electronic configuration of scandium will be 1s2, 2s2, 2p6, then 3s2, 3p6, then 4s2, 3d1. Okay, so you see, instead of 4p, that is after 4s, we are actually expecting 4p, but instead of 4p, here we have 3d. Because 3d orbital has lower energy than 4p orbital. That is here the 3d orbital is being, since it is being lower in energy than the 4p orbital, it is filled first. Okay. Now, consider the element chromium. Its atomic number is 24. So its electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We are expecting this electronic configuration like 4s2, 3d4. Because this is how the energy levels are, given as per the increasing order of energies, no? This is the expected electronic configuration of chromium. But the actual electronic configuration of chromium is this, that is 1s2, 2s2, 2p6, 3s2, 3p6. Instead of 4s2, we have 4s1. Instead of 3d5, we have 3d5. Okay, see, this is the expected electronic configuration of chromium, but this is the actual electronic configuration of chromium. Okay, and similarly, if you consider copper, its atomic number is 29. So 1s2, 2s2, 2p6, then 3s2, 3p6, 4s2, 3d9. This is the expected electronic configuration of copper. But the actual electronic configuration of copper is like this. Instead of 4s2, we have 4s1 and 3d9, we have 3d10. Okay, that is, instead of 2 electrons in the 4s orbital and 4 electrons in the 3d orbital, chromium has 1 electron in the 4s orbital and 5 electrons in the 3d orbital. Why? Because the fully filled orbitals and half-filled orbitals have extra stability, that is lower energy. So chromium adopt this D5 configuration. Similarly for copper, it adopt this D10 configuration because the half-filled and fully filled orbitals make atom more stable. So here this becomes a half-filled orbital. Here this becomes a fully filled orbital because in D subshell the maximum electron that can have is 10. So here we have half filled 5, half of 10. Here we have fully filled, so 10. So, the half-filled and fully filled orbitals make the atom more stable. So, that is why the copper and chromium, they adopt such configurations. Okay, thus, you see P3, P6, half-filled, full-filled. D5, D10, half-filled, full-filled. Then F7, F14. Because you see in F subshell, it can have maximum 14 electrons. So, half means 7. So, these are actually the configurations which are either half-filled or fully filled, and they are more stable configurations. That is, in certain elements such as copper and chromium, where the two subshells 4s and 3d differ slightly in their energies, an electron shifts from a subshell of lower energy 4s to a subshell of higher energy 3d, provided such a shift results in all orbitals of the subshell of higher energy getting either completely filled or half filled. See, the valence electronic configuration of chromium is 4s1 3d5 and for copper is 4s1 3d10. Okay, it has been found that there is extra stability associated with these electronic configurations. So, in this video, we have discussed about the electronic configuration of atoms. I hope it is clear to you. Thank you.